So in question 2, let's begin with the molecular formula issue. It's such a small molecule that you might almost think you could figure it out just from the spectra without this, but that's not the point. If they give you these data, you've got to use them. In all these kind of questions, if they give you lots of different sorts of data, you've got to make sure you explain all of them in terms of the structure. And so this is generally going to be where you're going to start. So, in a combustion analysis, the important thing to remember is that all of the carbons in your organic compound are going to end up as CO2, and so we can start out by recognising that the moles of carbon in this sample of B, the 4 gram sample of B, the number of moles of carbon in that is the same as the number of moles of CO2 produced when it's burned. And of course we can work that out because it told us this was at room temperature and pressure. As soon as you see that in the question, that acts as a prompt that says you can use the 24 dm cubed trick. Okay, so at room temperature and pressure, the moles of gas is equal to the volume in dm cubed divided by 24.0. So helpfully we've already been given the volume in the right units in dm cubed, so that's just equal to 5.73 divided by 24.0, which, if you divide it out, comes to 0.2388 moles of carbon. With the hydrogen, what we have to do is work out how many moles of water we've got. It's not quite as straightforward this time because there's 2 moles of hydrogen in each mole of water, so let's just get the moles of water first. So the moles of water is mass over mR, okay, which is 2.69 divided by 18.0, which comes to 0.1494 moles. Okay, notice all the time we're using lots of significant figures at the moment, only round at the end, and then you avoid getting numbers different from those the examiners are expecting by rounding at an earlier stage. So it was just a bit risky to do that. So keep lots of figures and round at the end. So that's the moles of water, but that's not the same as the moles of hydrogen, because each water contains 2 moles of hydrogen, or each mole of water contains 2 moles of hydrogen. So we can say that the moles of hydrogen is therefore 2 times the moles of water, which comes to 0.2989 moles of hydrogen. Now we've been told that there's nitrogen in this molecule as well, and you can't get the moles of nitrogen in this same kind of way, but you can get it because we know the total mass of the compound, and we can work out what contribution the hydrogen and the oxygen made to that, and therefore just by subtraction figure out what the nitrogen mass was. So we can get that the mass of carbon in the compound, we've got that many moles of carbon is moles times the relative atomic mass, so that's 0.2388 times 12. Okay, just using mass is moles times AR. Okay, so that gives us 2.865 grams. And we can get the mass of hydrogen. Again, is moles times that, which is 0.2989 times 1, which is 0.2989 grams. And if we add those up, we get that the mass of carbon plus hydrogen is the sum of those 2, which adds up to 3.164 grams. So that comes out of this total of 4, and the difference between the 2 numbers is the mass of the nitrogen. So we can get mass of the nitrogen is equal to the total mass minus the carbon plus hydrogen mass, okay, which is 4.00 minus 3.164, which comes to 0.836 grams of nitrogen. Okay, so what we then need to do is to turn that into moles, because then we'll have the moles of each element. So we've got carbon, we've got hydrogen. If we have the nitrogen as well, then we have everything we need to get the empirical formula. So we get moles of nitrogen is equal to mass over AR. Okay, so that's the mass, 0.836. And we divide that by 14.0 for nitrogen, which comes to 0.0597 moles of nitrogen. Now we can use this information, the moles of the three elements, to get the empirical formula. You don't have to set a table up, but it's quite a convenient way to do it, and since that's what we've always done with molecular formulae, we may as well, with empirical formulae, we may as well stick with that and just say, right, these are the relative moles, so copy those numbers down, so 0.2388, 0.2989 and 0.0597, and do what you always do. Once you've got to the relative moles stage, you divide by the smallest of them, because that, with a bit of luck, will turn these numbers into whole numbers. So you divide each of them by 0.0597 and you find that that goes to 1 and that goes to 5 and that goes to 4. So that tells you that the empirical formula is C4H5N. It's very important that you realise that's not necessarily the molecular formula, because all you can work out from this is the relative moles of each element, not the absolute number in the molecule. So make it clear that so far that's just the empirical formula. To turn that into the molecular formula, we have to use the mass spec result. And you've got to make sure you've made this clear. So the mass spec tells you that the molecular ion M over Z is equal to 67 in the mass spectrum, and you explain that what that tells you is that the MR of compound B is equal to 67, and then you just compare that with what that formula predicts. So you say, right, C4H5N, so 4 12s are 48 plus 5 is 53 plus 14 is 67. Okay, which agrees. So in this case, that means that this is the molecular formula as well. Okay, but it's very important that you show that working in there, because otherwise all you've calculated is the empirical formula and you're not going to get full credit. You know, if you carried on from there, then as it happened you'd have got the right answer, but of course, you know, it could have been C8H10N2 or whatever. You don't know that until you do that bit with the mass spec. So that's the molecular formula that we've got to work with. Okay, so now we've got the molecular formula, we can start looking at the spectra. So again, start with the infrared. So this looks quite different from ones we've mainly looked at, because the functional groups in it are quite different. So no OHs, clearly, because there are no big peaks at this end. There's no carbonyl either. You might at first sight have wondered if that peak was a carbonyl, because if you don't look closely, it looks in that right general region around 1600, 1700. But if you do what you should do and draw the lines down that mark the edges of the peak, you see that it's actually a very narrow range this time, and that isn't what carbonyls look at. You know that the carbonyl peaks are quite wide, so they go from about 1630 to 1820, so you know, almost 200 wave numbers wide. That's a much narrower peak, so it doesn't look like a carbonyl, and more to the point, the numbers don't add up. and if you look closely you see that it spans the range from about 1620 to 1680 wave numbers, and if you look on your data sheet that corresponds to C double bond C. In other words, it's telling you that there's an alkene group. So that's a common functional group. We haven't seen it that often in infrared spectra. That peak's sometimes difficult to see, especially if there's a carbonyl group, because it's so close to it and it's not usually as strong as the carbonyl group. It can get hidden underneath it sometimes. But in the case where there isn't a carbonyl group and you haven't got too many other peaks encroaching around it, that can be very useful. Okay, so look out for C double bond C, because that can be a useful one. And this one sticks out like a sore thumb because that's a region of the spectrum that's normally completely empty between 2000 and 2500. But again, if we draw the lines down to see what that range corresponds to, it corresponds to around 2220 to 2260. So again, a very sharp, narrow peak, and that comes from C triple bond N. Okay, so the infrared actually has been extremely informative in this case, because it's told us that we have an alkene group and a nitrile group. And again, it's important to register what that means. There is only one nitrogen in the molecule, and that's it. So that means we're not looking for NHs, so no amines, amides, anything like that. The nitrogen is a nitrile, and we know that clearly from the infrared. Okay, so that's what we know so far from the molecular formula in the infrared, and here's the NMR. So these two peaks are between 5 and 6 ppm. We know there's an alkene group in there, and that's consistent with alkene type hydrogens. So that tells us, because we've got two peaks in that region, that we've got two non-equivalent alkene hydrogens in the molecule. This one is between 1 and 2 ppm, which is just an HCR shift. So we've got three types of hydrogen, and we can get the areas, and the areas are actually very useful in this case. They've been mean here. Instead of giving you the actual numbers, they've given you this integral trace, so you've got to remember how to deal with that. So the trick is that with your ruler you just extend that baseline along there and you measure the height of that step. Okay, and then you do the same here. Extend that along with your ruler and you measure the height of that step, and finally you do the same again here and measure the height of that step. Okay, and you just measure them in millimeters, so you're going to get something like about 8 millimeters and 8 millimeters and 24 millimeters. And what you do is you just look at what the ratio is, 8 to 8 to 24. Well, if you divide them all by 8, that means that you have relative areas of 1 and 1 and 3 are the relative areas. Okay, so what that tells you is that the HCR peak has a relative area of 3, which means that there are 3 hydrogens, which is likely to mean a CH3 group. And these each have an area of 1, which is what we'd expect because we know we've got 2 non-equivalent hydrogens there. Okay, so that's extremely useful information, that we know what we've got in the molecule. The other thing that's extremely important is that all of the peaks are singlets. Okay, so that tells you something hugely important, which is that none of them have hydrogens on the adjacent carbons. So we should write that down, that all peaks are singlets, which means that there are no hydrogens on well, okay, no adjacent CHs, basically, is what it tells us in each case. And so that's going to make a big restriction on what the possible structures are. So if we start by thinking about the alkene group, what it means is that we know we've got two alkene hydrogens, and they can't be like that, because we know that they're not equivalent, right, because they've got different chemical shifts. But if they were like that, they would split each other, and therefore that's not possible. So what that means is that the only way we can explain having two alkene hydrogens which don't split each other is if they're attached to the same carbon. So where does that leave us? Well, we've got two things to stick on that end, and of course we now know from here that we've got a CH3, so that will be one of them. And going back to the infrared, we know we've got a CN, so that will be the other one. And that's our structure. Just check it fits the molecular formula. So we've got the 4 carbons, we've got the 5 hydrogens, and we've got the nitrogen, so it fits the formula. None of these hydrogens has an adjacent CH, because you can see for these two, the adjacent carbon is that one, which has no hydrogens. For these 3, the adjacent carbon is also that one, so no hydrogens, so no splitting. So it explains that. And the chemical shifts we've already talked about, and the areas we've already talked about all fit. So that is your answer. The thing that, because they were all singlets, you might almost not think about splitting. But just as in infrared, the absence of a peak is very important evidence. You know, there is no OH, for example, in a compound. In this case, the absence of any splitting gives you very important information that whatever structure you come up with, it can't have adjacent hydrogens as that would have. So that's the only possible answer.